Hello, Chemistry 30. This is our 6th lesson in the equilibrium unit. This is complex equilibrium problems. In this lesson, we will work through 3 examples. Example number 1. In a 500 milliliter reaction vessel at 900 degrees Celsius, carbon monoxide gas and water vapor react to produce carbon dioxide gas and hydrogen gas. Initially, 2.00 moles of each reactant is placed into the vessel. Kc for this reaction is 4.20 at 900 degrees Celsius. What is the concentration of the products at equilibrium? Pause the video and attempt this example. First, we have to create an ice table that includes a balanced chemical equation. The initial concentration of both reactants is 4.00 moles per liter. This is the 2 moles divided by 0.5 liters. The initial concentration of both products is 0 because they were not given in the question. There was no equilibrium value provided for any chemical species in the equation, so therefore we must assume that change is an unknown variable. Since we are starting with only reactants, the reactants must lose, and they will be minus x. Since we're starting with no products, the products must gain and will be plus x. At equilibrium, our concentrations of each species will be equal to the following. We can then write our Kc expression, which is equal to 4.20, and we can substitute our values at equilibrium. Kc is equal to x times x divided by 4.0 minus x times 4.0 minus x. We can then square root all values, the 4.20, the x times x, and the 4.0 minus x times the 4.0 minus x. That will give us 2.04 equals x divided by 4.0 minus x. We can assume that the 2.04 is over 1 and cross multiply. This will leave us with 2.04 times 4.0 minus x, which is equal to 1x. We have to FOIL the left side of our equation, which means we will take the 2.04, times it by 4.0, and then times it again by minus x. This will give us 8.19 minus 2.0x, which is still equal to 1x. We then have to bring both x values to the one side of the equation. When we take the minus 2.04x and we bring it to the other side of the equation, it becomes positive. This will give us a total of 3.04x on the right side of the equation, which we can then divide on the opposite side to solve for x. As a result, x is equal to 2.69 ... The concentration of both products is then equal to x, which is equal to 2.69 moles per liter. This is known as a difference of squares method. This is the only method we will use to solve for x in a Kc expression. Example number 2. For the synthesis of hydrogen fluoride for hydrogen and fluoride, 3.00 moles of H2 gas and 6.00 moles of F2 gas are mixed in a 3.00 liter flask. The equilibrium constant for the synthesis reaction at its temperature is 1.15 times 10 to the second. Calculate the equilibrium concentration for all of the chemical species. Pause the video and attempt this example. First, we need an ice table. The concentration of H2 gas initially is 1.00 moles per liter. This is the 3 moles divided by the 3 liters. The initial concentration of F2 gas is 2.00 moles per liter. This is the 6 moles, again, divided by the 3 liters. There was no value given for HF gas, so we must assume its initial concentration is 0. We were not provided with an equilibrium concentration of any chemical species, so we will have to make change in unknown variable. Since we are starting with only reactants, the reactants must lose. They will be minus X. And since we're starting with no products, the products must gain. They will be positive X. But notice it's positive 2X. This is because of the coefficient in front of HF gas, which is a 2. And if we think about the molar ratio in the chemical equation, the change for HF gas will be double the change of all other chemical species. At equilibrium, our concentrations of each chemical species is equal to the following. We can then write our Kc expression, which is 115 equals 2x squared divided by 1.0 minus x times 2.0 minus x. Unfortunately, we cannot square all terms in this equation, so we must move forward and cross multiply. 2x squared is equal to 4x squared, which will then be equal to 115 times 2 minus 3x plus 2x squared. We can then multiply the 115 by all terms in the brackets. This will leave us with 4x squared is equal to 230 minus 345x plus 115x squared. We can then rearrange our equation to get all of our values to one side, which will eventually leave us with 111x squared minus 345x plus 230. We will then have to use the quadratic formula to solve for x. Once we complete the quadratic formula, we will be left with two x values. One, which is 2.1397 ... and the other x value, which is 0.96838 ... Only one of these x values will work. Our first x value is too large, and if we substitute it in for our reactants, we will be left with a negative concentration. Therefore, we must choose our second x value. And when we substitute this in for all of our chemical species at equilibrium, we are left with a concentration for H2 gas of 0.0316 moles per liter. The concentration of F2 gas at equilibrium is 1.03 moles per liter. And finally, the concentration of HF gas at equilibrium is 1.94 moles per liter. Example number 3. 0.250 moles of NO2 gas were introduced into a 1.00 liter flask with an unknown amount of CO gas. When the system reached equilibrium, it was found to have 0.243 moles of CO2 gas. Determine the initial concentration of the CO gas if the Kc value is 146 at 500 degrees Celsius. Pause the video and attempt this example. First, we have to create an ice table. We were provided with the initial concentration of NO2 gas, and we were not provided with any values for the products, so we can assume that they will be 0. We are trying to find the initial concentration of CO gas, and we were also given the equilibrium concentration of CO2 gas, which is equal to 0.243 moles per liter. Since we have the initial and equilibrium concentrations for CO2 gas, we can find the change, which is plus 0.243 moles per liter. Once we know the change of one chemical species, we can find the change of all other chemical species in the equation. And since all species are at a 1-to-1 molar ratio, their change in concentration will be the same. Since the products are positive, the reactants must be negative. We can then solve for the equilibrium concentration of all chemical species, except for CO2 gas, which will be our unknown X. We need to solve for X, and once we solve for X, we can add back the change to get our initial concentration. We then have to write our Kc expression, which is equal to the products divided by the reactants. Remember, we are trying to find the equilibrium concentration of CO gas. So we can rearrange the Kc expression to solve for the equilibrium concentration of CO gas, which will be equal to 0.243 times 0.243 divided by 146 times 0.007. When performing this calculation, our concentration of CO gas, which will be equal to 0.0577 ... moles per liter. We can then add back the change. Remember, we are going from equilibrium to initial concentration, which is the opposite. So we must add back the change. And if we add back the 0.243 moles per liter, we will be left with an initial concentration of 0.301 moles per liter for CO gas. Moving forward, we will write the equilibrium unit test.